Foundation for Robotics (IHFC) was incorporated on June 13, 2020. About IHFC. Advances in sensing, computation, and autonomy are enabling robots and autonomous systems to enter real-world domains such as manufacturing, defense, medical, agriculture, etc., where machines must work alongside and interact with humans. We are entering an era of manned and unmanned teaming where humans and robotic systems must work together towards common goals. The four verticals of IHFC: medical, agriculture, industry, and defense. Our goals: human robot collaboration for enhancing human capabilities and reducing risk and improving productivity. Our objectives: research on novel technology areas of robotics and automation science, development of products for benefit of society, inculcation of startups, and promoting entrepreneurship in India. Our CQ: concept, collaborate, commercialize. From research to product. The grand projects of IHFC: medical simulator, human robot interaction control, rehabilitation robotics, drone applications, healthcare robotics, human robot interaction intelligence, intelligent sensing and secure communication, and Industry 4.0. Bird, a center of excellence at IIT Delhi. About Bird: biologically inspired robots and drones. The Center of Excellence on Bird, Biologically Inspired Robots and Drones at IIT Delhi is an evolution from its humble research activities, which began a few decades ago by its faculty drawn from the Department of Mechanical, Electrical, and Computer Science Engineering. Bird has 10 plus projects, industrial and academic, 27 plus members including faculty, students and technical staff across various departments of IIT Delhi, 150 plus publication in international and national conference and journals, 9 years of experience. Cognitive Science Program, a Department of Humanities and Social Sciences at IIT Delhi. Cognitive Science Group at IIT Delhi is to create a knowledge pool that can address relevant problems under the ambit of human cognition both for India and the world at large. It helps students acquire a strong background in theoretical frameworks and empirical approaches of one or more areas of cognitive science. Cognitive science is an emerging new field of study that endeavors to study the mind from multiple perspectives and disciplines by combining ideas, principles, and methods from psychology, linguistics, philosophy, computer science, and neuroscience. This knowledge is applied for developing a better understanding of how our minds, brains work while creating better products, tools, services, and policies. CoboTalks, leading the way in the human robot collaboration space.
Say hello to the fastest prosthetic hand, called Enrich, developed in the Embedded System and Robotics Laboratory Tezpur University, India. Enriching the life of upper limb amputees, the prosthetic hand has features such as fast as human hand, easy interface, anthropomorphic, ergonomic design, powerful grasp, low cost and lightweight. Grasping by Enrich is tested with different objects. User's intention of grasping an object is collected as EMG signal generated from the muscle. The embedded controller processes the EMG signal and makes a decision for grasping. We have also experimented the weightlifting capacity of Enrich. On recognition of grasping intention, Enrich grasped the water bottle. This was repeated for 10 trials. During each consecutive trial, the volume of water in the bottle was increased by 50 milliliter. It has been observed that Enrich could lift the water bottle up to 9th trial and started slipping on 10th trial. The weight was measured in a weighing machine after the 9th trial, and it is found that Enrich can lift up to 450 grams. After successful laboratory testing, Enrich was tested with 8 upper limb amputees in the Regional Institute of Medical Sciences, Impal Manipur and Times Hospital, Tezpur, Assam. In this clinical testing, it was seen that the user could grasp different objects using Enrich. Feedback from the users were also collected in terms of design, controllability, usability, color, ease of use, comfort. The prosthetic hand was then improved based on these feedback. Following the successful completion of the clinical testing, the pilot testing of Enrich was carried out with 2 users. The prosthetic hands were fitted to the user's residual limb with the interfacing socket. Enrich was used by them to carry out their daily living activities. Regular feedback has been collected since the fitting of Enrich. Thank you.
Thank you so much. Thank everyone for joining in, and very, very good evening to all of you. Today, CIP Abasu welcome you warmly, and today introducing you to our very, very esteemed speaker. I had the privilege of meeting Professor Nayan a little while ago, and his remarkable work in rehabilitation was fascinating, and I had the opportunity to actually see this biohand firsthand in Tezpur University itself, and it was a beautiful experience. So it was always my dream to have him come on CoboTalks and share his knowledge and what he's working on with people who are interested, because medical rehabilitation is a big thing, and it is he's working towards the benefit of working towards a cost benefit and cost beneficial, and things that are accessible to everybody and not just for the elite, and which is what I really honored in his work. So Professor Kakoty actually is an electrical engineer from Johar Engineering College. He also holds a Master's of Technology in Bioelectrics and a PhD in Rehabilitation Robotics, and that's also from Tezpur University. He was in City University in Hong Kong, and where he did a postdoctoral fellow in 2014. Currently, he is the professor in the Department of ECE in Tezpur University, and he leads the Embedded Systems and Robotics Laboratory at Tezpur University. He is a IEEE senior member, and his primary work focus is development of artificial hands for upper limb amputees. And he has already completed many consultancy projects, and he's also a part of IHFC grant project, which is ongoing with us in the area of biomedical engineering, which is of course aiming for an advanced prosthetic hand, which is what he's going to do today. His work is implemented in the wallet. I mean, got what you call a lot of awards and recognition from various government and other faculty members. Today, what he's going to be presenting to you is a prosthetic limb and hand that he wants to talk to you about, which will focus on the journey from the development of this very low cost EMG controlled prosthetic hand, which he's working at Tezpur, leading to the completion after the clinical testing and undergoing pilot testing. It will cite indigenous prosthetic hands vis-a-vis a very commercial version, which are very expensive and available from the international scenario. So this is completely indigenous and made over here under his supervision. Emphasizing the contribution to the service of the individuals of limb amputation in India, which is a large percentage actually. This talk will also include a glimpse of recently stated work that he has started on brain-computer interface-based control on the prosthetic hand. With that, I would like to hand over, let me see, do we have our IHFC CEO, Ashutosh, have you joined it, sir? Ashutosh, are you in the... Okay. If he has... Oh,
good evening.
Okay,
Welcome, Professor Kakoty. I'm sorry, the camera has an issue, so it's only my voice. But I'll maybe come to Tezpur to showcase you my piece. Oh, it's working now. So pleasure to have you here.
Good evening. Good evening, all.
Yes, we have high hopes from this product, Enrich.
Yes, let's see how far we can go and translate it from lab to the market.
Right. And I think all the students are also eager to learn, so I would not make them wait for longer. Thank you so much for being a part of this. Thank you, Pia.
Thank you, sir. Thank you. Hrithik, we'll play the IHFC maybe a video a little later. We will go on with the talk right now, and I will hand over the platform to Professor Nayan, so that all the students who are waiting here eagerly to hear what's the next revolution in prosthetic rehabilitation work in medical sciences. I think I will hand over the field to him. So please, Professor Nayan, it's all open to yours.
Yes. Thank you very much, Madam Pia, for the introduction, and to IHFC for giving me the opportunity to present my work today here at the CoboTalks. So, I hope my slides are visible.
Yes, sir. They are visible.
Okay, thank you. So let's start with it. So I basically belongs to the place in the northern region of our country. This is the map of our country. And in the northeastern regions, in the central, the Tezpur is there. On the bank of river Brahmaputra in the valleys of the Himalaya, surrounded by a lot of tourist places like National Park Kaziranga, and is an historically very rich place. So I welcome you all present over here to our university, to Tezpur, and to visit our lab. So in this university, we are working in the lab, or I'm leading the lab called Embedded System and Robotics Lab, in which currently the project is being funded by IHFC. We call it in short as the Enrich. And we find here the interest into the area of rehabilitation robotics, and basically we focus into the upper limb prosthesis, as Priya Madam has already explained or briefed it to you. So today I'm going to talk about the prosthetic hand, the commercial versions across the world, the Vis-A-Vis, the TU Bionic hand, TU that stands for Tezpur University. So on this slide, on the top, we can see the advanced versions of the prosthetic hands. One is from the B Bionic from Ottobock, And the limb from the Osur, currently it is procured by Osur. Earlier it was by Touch Bionic. So these are the hands that we can see over here. And towards the lower side of the slide, we see the prosthetic hand that is being developed in test winners. So how we reach to up to the development of this prosthetic hand that we can see in the lower side of the slide, that is what we will be talking in another 45 or 50 minutes. So to start with, let's have a case study.
आने का टाइम वो मेरा हाथ में सोल पहना था, फिर वो सोल में बुलेट का चेन में अटक गया, तो फिर मैं उधर से गिर के फिर हाथ पूरा ये निकल गया था। फिर उधर से डांस हॉस्पिटल में ले गए, फिर उधर में ऑपरेशन किया था। ऑपरेशन ठीक नहीं हुआ, फिर उधर से जाके फिर IHFC हॉस्पिटल में ले गए, उधर में 2 ऑपरेशन करके उधर में ठीक नहीं हुआ, तो इंजेक्शन हो गया था हाथ में, फिर उस वजह से फिर हाथ को काटना पड़ा। हाथ काटने के बाद बहुत प्रॉब्लम हुआ था। फिर टेस्ट यूनिवर्सिटी ने सालों के साथ कांटेक्ट किया था, तब सालों ने हाथ दिया, उसको हाथ को डेली इस्तेमाल करती हूँ और वो हाथ लगा के अभी अच्छा लग रहा है। स्कूल यूनिवर्सिटी का सालों में ये हाथ दिया है और डेली यूज करती है इसको, काम करते हैं।
So there was a lady in the age of 23 years who lost her upper limb and above elbow part in a road accident, and at the same time we were also coming up with the clinical testing of our hand that we call as the enrich. We took her as one of the subjects into our research, and she also had become a part of the pilot testing for the hand. So before starting with this journey, let us understand what is actually the hand amputation. So what is this loss of the hand? Hand amputation is the loss of the our natural hand at different parts, or different sections. It happens basically below elbow, or sometimes it is above elbow, or at the arm level. So we categorize it into 3 basic categories, calling it as the transradial, those who have lost it below elbow section, and then transhumeral, who have lost it above elbow. Above elbow again comes at the arm level or at the shoulder level. And then there is another group, congenital, who are not having the hand from the birth itself. So in our country, if we see the statistics of these amputations, then we found that 80% of these amputees belongs to the rural area and 20% from the urban. And surprisingly, they are in the age group. 30% of these people are in the most valued age group, that is 30 to 44, where people do the work more efficiently. And 79% of them are into the male category. And the statistics of 2011 says that there are around 54 lakhs of amputees, and every year this number increases by around 25,000. But the experts currently says that this number is much more higher in our country. And the reasons why or how the people loses their hand are because of these road accidents. These are the real cases that we have taken into our study. Now people loses their hand in the incidents like road accidents, or because of the electrical shock and then the burning. So the cause of this hands loss brings different kinds of challenges for them to operate the prosthetic hands, which we will see. So when the person loses their natural hand because of these different causes, then what the alternatives left out to them? So if we see it in an international scenario, then there are advanced prosthetic hands which are available, that can replace this missing hand in the human body. So Michelangelo is one of the hand that is from the Autobot, is one of the most advanced hand let's have a view of how it works. We can see a very nice finishing or the design fitted into the amputee.
Can you pick something or something?
So they do some adjustment of the wrist manually for gripping different kinds of objects depending on its shape or size. But the fingers are controlled electrically through actuators. So in comparison to this international product from Otobo, if we see what is nationally available in our country or indigenously available, then we found that it is in 1999 when the researchers from IIT Bombay and CMC Vellore, Christian Medical College Vellore, have come out with a motorized hand. And then currently, Elimco, Artificial Limb Manufacturing Corporation of India, so it's in Kanpur-based NGO. So they are developing the different parts of the prosthetic hands, which they give to the amputees for user. And this is one of the hand that you can see in the video. The person is being fitted from Elimco, and he is trying to pick up this piece of wood, which is the cover to the box, and trying to place it on the top of this box. So by looking at these two consecutive videos, we can realize kind of the controllability that we have with the advanced versions and the kind of functionality and controllability that we have with the indigenous versions. This Elimco hand is basically cable driven, and the amputee needs to pull that cable with his remanent muscle strength. So there is a gap in terms of the technology. If we see these indigenous versions vis-a-vis the international versions. But to mention here that currently some of the startups are coming up who are trying to develop prosthetic hands that have better controllability, and some of the industries are there who are taking these international variants and selling it in our country. So if we look at this scenario, then we need to actually understand what is the need of our people, how we can give them a better controllability or functionality, and at the cost of the what. So if we compare this international version vis-a-vis this our indigenous versions that are currently present, then we see that there is a gap in technology which comes under this quadrant. And on the top of that, what are the things that we will be requiring for taking it to the really international level that is that it will be accepted in the worldwide. So we need a very good quality which we can call globally accepted. Then the packaging of this, and as the products are already in the market, so we need an aggressive kind of marketing. We need to establish the brand for this, and for that, how we are going to provide the after sales, what will be the services we will be providing after sales, and how we can go ahead of the prototypes or the prosthetic hands which are available currently in the market. So if we see that to accomplish all these three quadrants, we need to define which extent, to which extent we want to provide this service, and at what quality level, and most importantly the cost. And another factor that we need to consider is the technology and the user. I may develop a very high-end technology over here, but if user is not very much familiar with it and he cannot use it, then finally no one will be there to take that technology. So these are the things that we need to keep in mind, and while keeping this in mind, we started working in this first quadrant. So with this aim, in 2011 and 12, and again in 12 and 13, we started some projects with the students. In the top of this slide, we can see a three-fingered hand, which is actually customized with angle sensors. The joints, these are having two links, and the base link joint is customized with angle sensors, and the tip of these are customized with touch sensors, tactile sensors. And this was being controlled by detecting the intention of grasping from the EMG signals, that is the electromyogram signals that gets generated in our body when we start some locomotion. So that is one of the projects being started with the BTech students, where these EMG signals are being stored into the system, and then in the system computer, it applies some classification algorithms to detect whether the incoming EMG signal is for grasping or opening the hand, and then accordingly it controls this three-fingered hand. We tried to develop it with customized with the sensors, applying the PI controllers over there. Following that, in the next year, we tried to go a more detail of how to mimic the human finger exactly, and the movements that it will have, or in terms of these phalanges or the joints, and then the torque transmissions, how the force or these joints are being actuated, how the force is being transmitted from the muscles to the joints. So taking that into all those into considerations, this project, it tried to equate the EMG signals while the subject, if we can see in the video lower of the slide, we tried to equate the EMG signals while the subject is performing the finger movements. In our finger movements, we do basically two types of finger movements. One is the flexion extension, like this we do, and the another one is the abduction adduction. None of the prosthetic hands in the market currently available can perform this abduction adduction movement, but the mechanism that we have in this particular finger, it can perform the abduction adduction movement. And this finger also was also being controlled through the electromyogram signals. These are the electrical signals that gets generated in our motor units, and as our body is conductive, they propagate through the muscle layers of the muscles and becomes available on the surface. So we can collect them non-invasively, and by collecting them, and then after processing, we can identify the intention for which these EMG signals are being generated out. So once that intention is being identified or recognized, then the particular movement we try to emulate into the finger. Here we can see that finger is performing the flexion extension operation. So yes, so following this, we went for development of a complete prosthetic hand, that is the five-fingered hand, a artificial hand prototype, a five-fingered hand. And this video is showing some of the steps that is being taken out for the development of that hand. It was in a very initial stage during 2008 to 14 that we tried to do. At that time, technology was not that advanced. No, during the last 1 decade, we have seen a shift in the technology. That time, the kind of 3D printing or no PCB printing was not available. So we had to use the traditional workshops, mechanical workshops for the developing each and every part of this hand. So we choose the nylon as the base material for this after a material comparisons. Then all these parts of the hand were developed using the traditional machines that usually available in an engineering workshop. So using the vice, we did this marking, and then for giving the shapes like the fingers have, we used to use this. We had to use this grinding machines.
There is some noise from somewhere. Can everyone please mute themselves? Can everyone please mute themselves because there's some noise coming time and time again. Except for the speaker, please everybody mute yourselves. So please
and
continue.
then and then to transmit the torque from the actuators, that is the electrical motors, to these phalanges, we have used it, try to replicate the tendon mechanism that we have in our hand. So for the tendon mechanism, we need to do these drillings to pass these lobes, and then finally this kind of shapes that we develop, and then we customized that with these actuators and then the power supplies which were in the standalone things, and as well as the driver circuits. But although it may look quite intuitive or being done in a using very traditional machines, but we followed their a scientific approach. We tried to study the biomechanics of the hand, what are the expected properties in a prototype if it needs to replicate the human hand, like the musculoskeletal structure, how will be the grasping manipulations will be done, how should be the functionality in terms of the degrees of freedom it should have, how should be the control or the drive mechanism it should have. Then it depends on the next step was the material selection. What kind of material we'll take, nylon, Teflon, like that. We gathered a group cluster of materials from which we have selected the nylon, depending on its specific gravity, frictional property, temperature, or which standing capacity, and then water absorption or rejection capacity, then followed by that development in the workshop. And for the control of it, we the mechanism that or the architecture that we followed was into the two groups. One was the superior hand control, followed by a local hand control. The superior hand control was basically responsible for the recognition of the grasp types that person was attempting. We used 4 EMG channels on the forearm of the healthy subjects, and then tried to understand the 6 grasp types, which one the subject is trying to attempt. These 6 grasp types that we can see on the figure over here being replicated by the hand, are the grasp types that is used during 70% of our daily living activities. So from these EMG signals collected while performing these 6 grasp types, we used at the time the support vector machine with K-fold cross validation for identifying the grasp types. And then once this grasp types is being identified, it was being followed by a local hand control, which was responsible for transformation of these grasp types into the actuation of the fingers, and considering the kinematic and dynamic analysis, which gives the grasp primitives and which are being fed to the PID controller for control of these prosthetic hands, or basically the motors that were present in this hand. So here that the first hand that we developed, the functioning we can see in this video. The EMG signals that were collected were stored into the machine. It was an offline control, and those EMG signals were processed once this graph type was being identified. Once this graph type is being identified, that command is being sent to the local control unit. And in this case, this power supply was also in a standalone big power supply we used. And we tried to replicate or emulate these 6 graph types. So for the sake of time, I'll be just skipping it here. So it was the story kind up to 2014, and this was the part of my PhD work. And then we move onwards that how we can make a more advanced hand which can actually sense the object and grabs it without breaking or without slipping it. So we had to put the sensors for that purpose. We put tactile sensors for this purpose at the fingertips of this prosthetic hand prototype, and then these joints were coupled with the angle sensors. We applied the PID controller into the hardware, and complete system has been made it without the computer in real-time control. Earlier, what we have seen that we were storing the signals into the system, processing them, and then trying to control the hand. And in this case, what we tried to achieve is the real-time control when the subject is performing the graph's intention that we tried to control. And this hand could grasp or perform 12 different graph types that are being found in the Kakoty's graphs taxonomy. And by the time we try to develop this hand, the technology has advanced. 3D printing has come, so we could have designed the hand in the software and then can easily print it with no more. We need to go to the mechanical workshop and do all this tedious work. So the control architecture that it followed, know how we could replicate the 12 graph types. Even it can replicate more graph types if we program it for that. So the control architecture is such that it acquires the EMG signal and tries to identify the intention, whether the person is trying to grasp or not. From the EMG signals here, we are not trying to identify what kind of grasp it is attempting. We are just trying to identify whether the person is attempting for grasping or not. And the type of grasp is being fed to it from an Android application separately. And these two informations were merged, and then we fed it to the lower level controller or the local controller, which is customized with these force sensors and the kinematic sensors. And then following a very interesting sleep detection algorithm, the hand was being controlled. So this is some of these results that we schematically represent. Here we can see the generation of the EMG signals is happening, and at the same in the next instant of time we get the signals from the force sensors as they establish the contact with the object to be grasped. So we continuously keep collecting or observing these force signals and taking the measurement between two force instances. We decide whether the angle should be increase or decrease in order to avoid any slippage of the graph object, or in order to avoid the breakage of any object that hand is trying to grasp. So here is a working video of this hand.
start phase of the app, you could see connect, disconnect, and manual open button along with the graph type. When a graph type is selected, it is transferred via the Bluetooth model to this prosthetic hand. The graph type is stored in this microcontroller. The raw EMG was collected from the user. Whenever there is an MSD to detect, this is the EMG unit for processing the EMG, and then this controller will use this EMG for finite state algorithm. Whenever an extraction was to be done, the PID controllers will actuate the DC motor inside the palm. When an object is grasped by the prosthetic hand, these force sensors will assess the force and send it to the controller for detection of slip or higher forces. This is the power supply for this hand. Similar to the Bionic hand 2.0, we have also experimented with the Bionic hand 3.0 for holding objects like cricket ball, we have changed the grasp type of grasping objects like Rubik's Cube. We use the same grasp type to grasp an egg. We could see that the hand was able to grasp the egg without breaking it or slipping it. Similarly, the cookie was also grasped by the hand without breaking. The grasp was done large diameter, small diameter, medium wrap, abducted thumb, light tool, thumb 4-finger, thumb 3-finger.
So while doing with this hand, the control and as expected, without slippage or breaking of the objects, we could have achieved, and it was we have another achievement was that we could have implemented it in real time, and it can perform multiple grasp types. But putting all those electronics hardware along with the power supply inside the sleeves of the hand was a challenge. So we make a trade-off between this functionality and the real applicability of the hand. While trying to doing that, we have come out with the hand that we call actually the ANRIDS. ANRIDS is the abbreviation for the EMG control prosthetic hand. So after doing the trade-off of these technical features as well as the applicability of the hand or usability of the hand by the user, we come out with the hand that we can see on this current slide, that is gripping the different objects and being used by the subjects. And this video will show the development process of this ANRIDS. All these parts are being printed in 3D printers.
For 4 objects like telescope, coffee mug.
So this hand is also being controlled in real time. When the subject generates the EMG signal by actuating the muscles or expressing the intention for grasping, that signal is being fed, which we call as the EMG or the electromyogram, being fed to the controller, which is fitted in the sleeve. And then the actuators being fitted into the sleeve itself also controls the mechanical parts of the hand for grasping operations. So initially it was tested in the laboratory environment.
The water, we increase the water level. appropriate way to find the maximum weight carrying capacity of the prosthetic.
So followed by this, we take the next step of this development, that whether this hand can be controlled by the actual users or who are amputees, no, who have lost their hand. So for that, we have collaborated with the different organizations, no, and our people have visited to RIMS, Regional Institute of Medical Sciences and Medical Sciences in Manipur, and they have started testing the hand with the real subjects.
DC says application forms can be downloaded from the website www.imphal.nic.in.
The
Relief Center for Welfare of Differently Abled Persons, Manipur, signed 5-year-long Memorandum of Understanding (MOU) with Electronics and Communication Engineering Teespoor University today for facilitating its electronic robotic prosthetic hand persons without limbs. According to a video released by the center, Women and Child Welfare Officer of the center, P. Victoria, said the agreement was signed after Teespoor University's prosthetic hand trial was deemed successful. In today's MOU signing event, Center Vice President Lenin Birong, Project Consultant Vikram Purohit.
So the lower video is showing the testing with the real subjects, and when we took this hand, we gathered feedbacks from these users that how they wish this hand to be if they need to use it during their daily living activities. And another challenge was there that know how this socket interface, how this hand will be fitted. Now this hand was kept separately, and we took the EMG signals from the subject to control the hand. But when they have to use it in their daily living activities, we need to use they have to keep it fitted to their body continuously. So how this interfacing socket can be developed, because different people are having different limb sizes and their remnant muscle size and shapes are also different. So that socket development is another aspect over here. But along with that, we took the feedback in terms of how easy it is to use or the comfortability level, how is the response time or the grasp power that they are getting, whether they are liking the shape or not. Most of the users have given the feedback they don't like the shape. Whether they feel any uncomfortability while placing the EMG electrodes, there we were a little bit in the better side. Then how much torque they required, whether they feel and any pain while using their hand. So in terms of these parameters, we have collected the feedback from this the demographic of 6 test subjects, which involve the causes of amputations from burning, accident, and then electrical shock. And then we came back, we had the discussions with our medical practitioners, and I am thankful to the funding agency that they're organizing the review meetings from time to time, where we get the feedback from the experts, and combining all this, we again redesign the hand. And the redesigned hand we can see in the lower part of this slide, along with this socket. The socket we tried to develop in a way such that this socket can be fitted to a variety of limb sizes. And then with this improved version of this hand, we did a clinical testing again with one of the subject who was having the amputations within the year. And this is some glimpse from this clinical testing of the subject. Again, the team has moved to the hospital who has given us this ethical permission for doing these clinical studies. Here the subject was in the initial first stage of the using this hand, is trying to express her intention through the EMG signals. So this was the first try that the subject tried. So this, while developing this hand, the core parts were the embedment of these algorithms, intention detection of grasping, and then controlling the actuator present in the hand for the movement of this mechanism, mechanical parts present in the hand. So the embedment of that was one of the aspects. We need to take care of that. It should have a good accuracy while performing these grasping operations. Also, the time being taken for performing the grasp type from the generation of this intention for grasping should be within a no satisfactory level. In case of our human beings, we perform any grasp types from the point of our thinking in our mind within a period of 300 milliseconds. And we and this hand happened to be satisfying that neuromuscular constraint. So we had that our second patent on that. And another interesting aspect that we have come across, that for embedding the things or making it more user applicability, we have taken off these sensor parts in this hand. But we have seen that while doing the analysis, that success to EMG in terms of success to EMG intensity ratio, we have seen that to maintain the grasp stability or to have a higher accuracy, the person varies his EMG intensity accordingly. So there is a feedback actually is happening in this case, which is through our visual systems. Like in the natural systems, it happens. That also gets reflected. That the subject is trying to vary his efforts while grasping different objects by this artificial hand, such that it does not fall, or they maintain a good accuracy while grasping. Then this is the third case that is from the group of the congenital. This is one of the subject from Silser that we have invited, and then this subject is actually not having his right hand from his birth itself. Then we did all the measurements, and to his measurements of the normal hand, we developed this one artificial hand for him, and he has done this first clinical testing. And this time we have done it in our lab, as the medical practitioners authorize us to do it. So while doing these experiments with the real subjects, we have been able to claim that our hand is advantageous in comparison to the market products that are available currently, in terms of the weight, in terms of the comfortability of using, or in terms of the time required for performing a grasp types. So these are some of the advantageous features that we have. So followed by that, two of the hands we have given to two subjects who are using it for last more than 1 year now in their regular activity. These are the two subjects, one from Manipur and one from Tezpur. So the center video is showing the fitting of the hand to the subject who is an above elbow amputee. So when we first fit the hand, then we see whether she is being able to carry it or feeling any uncomfortability or how much easiness she is having while using that hand. So this is the pilot testing that's going on, and the promo video that you have already seen here. One thing is different is here that weight carrying capacity in the prosthetic hand that we have, that you have seen is of 500 gram. But while iteratively developing this hand, currently our hand can carry up to 2 kg. This is a water bottle, 1 liter water bottle being filled.
Trial 3, 2 water bottles, both half filled with water. Trial 4, 2 water bottles, both fully filled with water. The results of the experiment demonstrated Enrich's lifting capacity. Enrich could successfully lift 2 fully filled water bottles. After conducting the trials, the weight of the water bottles lifted was measured using a winch. The accumulated data revealed that Enrich could lift a load of at least 2,150 grams.
So this is all about what I wish to share with you. And regarding that BCI controlled prosthetic hand, I hope in future I will cover that, because EMG controlled prosthetic hand itself is a very vast thing, and I could have somehow make it in time. So we have very nice people working with us all along from the social activities, from the management group, and then from technical group, or from the medical sciences. And we always pride of the things that are being developed indigenously, and we are also trying to do something in that line. My lab members, some of them might be available online here. They can switch on their camera to show. And I would like to express my thankfulness to all of you for being here by using the another indigenously developed product from our country, that is the Robo Analyzer. It's a robotic learning tool being developed in IIT Delhi. With this, thank you all. And I am open to any queries or to address any questions.
Thank you, Professor Kakoty. This is Udayan here, and probably Pia is. She
Sorry,
has
sorry, I
some.
was
Yeah,
in a meeting.
Please
I just
go
got
ahead.
back.
Yeah.
Yes, thank you, Professor Kakoty. That's very. As I told you, was always impressed with what I'd seen when I'd visited you. So I am sure there are some questions which people would like to ask you. So if anybody has any question, please raise your hands or put the question in the chat box. And Udayan, can you just let us know?
Yeah, sure.
I have a question. I have raised my hand.
Oh, yes, yes, Professor. How are you? Good evening.
Good evening. Nayan, most of the videos I see the prosthetic hand is separately kind of shown to do some action. Wherever some people are wearing it, hardly there are any experiment with that thing? I mean, what is the reason behind it?
When the people is actually wearing it, currently they're using at their home. So we are collecting some videos from time to time. Yeah, we can.
So maybe those, when you say trial 1, trial 2, trial 3, trial 4, for example, the heavy weight, for example, right? So maybe okay, you do it for some data collection, everything, but in a public demonstrations like this kind of forum, maybe real life use also would create a better impact actually to the people's mind. That's my suggestion. Okay.
Thank you.
Thank you. Also, we, I think, have a question in the chat box. Shweta is asking, are EMG signals, are they that strong to use?
Yeah, thank you for this query. EMG signals are in the range of millivolt, microvolt to millivolt, and it varies from subject to subject as we collected the non-invasive ones. So our skin conditions are also different, and the noise factors that arises because of this noise, external noises, are also different. So these EMG signals strength is in the range of microvolt to millivolt. So they currently they directly cannot control. So they give the information. Once they give the information about the type of the grafts, then emulating it into the prosthetic hand is by a lower local hand control. So that local hand control is being powered by the external power supply.
Okay, and that also helps to reduce the sorry, sir, and that also reduces the noise, because she also wanted to know how the noise is removed.
Yeah, for that, first of thing is that we need to clean the skin. We need to clean the skin with alcohol wraps cream, and then because the skin develops some impedances for the signals to go from the user side to the machine side. From the human to the machine. So for that, first we need to clean and appropriately place the electrode on the specific muscle. Then after that, once we get them into the memory, whether it is a computer or into a microcontroller chip, we need to do the pre-processing on it. And then during the pre-processing, we apply filters like the bandpass filter, and then to remove the power line, we apply the notch filter. And on the top of that, we apply the instrumentation amplifier to increase the magnitude for appropriate recording and displaying of the signal. So while applying this instrumentation amplifier, it comes with a specific parameter called common mode rejection ratio, which also rejects this noise level. So these are the different levels at which these noises are tried to cancel out before feeding it to the algorithm to detect the type of grafts.
Does that answer your question? I hope, Shweta. There's another question from Ibhan. Ibhan asks, how do you calibrate the actuators for speed and the force that they're applying? And what are the countermeasures against slipping? How is the range of motion defined unless and until it's done in the hardware itself? So they're like two
Right.
in one question.
Yes, yes. So the EMG, that force, there are actually two questions. One, the first part is that how the movement is proportional to the intensity of the signal. Am I right? Can this person who is asking the question speak about it?
Yes, sir.
Yeah. Maybe you can unmute yourself and ask the question. Ibhan,
Yes,
are you
sir.
there?
I want.
Yeah.
Yes, sir. Yes, ma'am. So my question was, how do you actually control the speed? Because that will be decisive in the force that we're applying. And if we're holding a sensitive object and suppose we click the finger too fast, then it might damage the object.
I
How
could not
do we
get your
prevent?
second part, but the first part, the response to is that how we control this force is the proportional control. The EMG intensity after crossing a particular threshold level, it increases if we apply more force on the muscles or performing more powerful grabs. So that EMG integral, if we take, then it gives a proportional by applying the proportional control, we can control the force applied during the grasping. And what was the second part?
Ibhan, can you repeat your second part of the question?
Yes, ma'am. So I was saying that suppose sometimes while we're holding something sensitive, we might apply too much force with the fingers and damage the object. So that can happen even with a normal hand, a non-prosthetic hand. How do you control that in prosthetic hands?
Right,
Especially when
right.
the material can damage it directly.
Right, right. The hand and that you have seen that users were using in their daily living activities, it is not having that feedback. But the hand that I have shown previous to that is having that control. While grasping an object, uh, without making it to slip, we need a minimum of 3 Newton force. So we that slip detection algorithm that I have mentioned tries to control the fingertip forces as well as force applied from the palm in and around 3 Newton. And if the slip is happening, then the tangent of that force, the change in or rate of change of that force varies, and that indicates the starting of the slip. And then, according if that change in or the starting of the slip is being detected, then the actuator changes the angles of the joints such that it does not slip.
Okay, so thank you.
Okay, does anybody else have a question? Kindly unmute yourself and ask. Okay, because the best question, we also have an Amazon voucher reward. So if your question is good, we will analyze that and we will reward you with an Amazon voucher. So if anybody has a question, don't hesitate if you want to visit an Amazon voucher and get your question answered. So why don't you go ahead and ask? Okay, nobody else? Okay, then I will take this opportunity to hand over to Professor Saha to kindly thank Professor Kakoty for his talk today, and also hand over our Springer voucher to Professor Kakoty, thanking him for gracing us with his presence.
Thanks, Pia. So thank you, Nayan, for sparing your time and sharing a very elaborate indigenous development. I myself personally very impressed that you have been working on this, and I'm sure this has been an inspiration to many of the youngsters who have been listening into this lecture from you. So congratulations, keep doing it, and our dream should be, one day, everybody in the world should praise. Yeah, prosthetic hand India से आया है सबसे popular है. So with all those dream, let us count that day. Till then, for a token of appreciation from our IHFC side, 150 euro coupon voucher sponsored by Sprinter. So please accept it from our side.
Thank you so much, sir. Thank you.
Thank you.
Sahas.
Thank you. Thank you.
We will be setting up the voucher to you shortly.
Yeah, I'm done. Thank you, Pia.
Okay, thank you, sir. Professor Nayan, I have one question from a little bit of a marketing perspective because that's what I take care of. To make this prosthetic hand a little more aesthetically appealing, so that one, as a human being, already is aware that they have an amputated arm. Second, to wear an arm which looks like doesn't look like real or doesn't feel real. Are you working towards that so that a person who takes it on will be more acceptable to wearing it and then buying it and promoting it further?
Right, right.
So the looks have to, I was just looking at them, it still looks a little bit, which you call prosthetic like and rubber like to me. So are we working aesthetically towards the design with any product design or anybody to, make it look a little bit more wearable?
Right, right. I could get this question because same we got it in the first feedback also after the first clinical trial. When we took it for the use by the users, no, they mentioned that we already don't have one hand, and why we would like to something which looks like a robot, and it makes brings more uncomfortability to them. So we tried to develop, redesign the thing, and we tried to put the skin colored glove on the top of that. But after doing that, people acceptance has increased. But still, there is scope for the further development in terms of this aesthetic look, or what we call it as the human-centered design. So for that. Further development into that, we are looking for collaboration with these design uh, experts, or might be the industries who takes it for manufacturing, and they have more experts into the designs or for the development of the aesthetics of these products. So we are exploring on into it.
Ah, great. Good to know, sir. Thank you. That was all. If anybody has anything else, Professor, can you put your email ID in the chat box so that if anybody who has questions in their mind and they can note down your email ID right now and write to you later, asking your queries.
Okay. It is easy to find me. Uh, I am putting my
Yes.
mail ID.
Yes. Yes. So everybody, it is Nayan. That's Nayan .robotics. That's ROBOTICS @gmail.com. Nayan.robotics @gmail.com. So